Hi, my name is Andrew Kuhn, and I'm a professor in electrical and computer engineering. And today I wanted to introduce this idea of using pupil diameter as a measure of cognitive load. So, in my lab, in the human computer interaction lab, we use eye trackers to understand human visual behavior as well as pupil diameter changes as, as users interact with various computing devices. And as it turns out, pupil diameter can be used to assess how difficult some of these interactions are. Here's a really interesting paper back from 1982, so this is clearly not all that novel knowledge, right? But it's been used for a long period of time now, and the 1982 paper is actually an overview paper of how this so-called task-evoked pupillary response is related to processing load and also what the brain looks like, so the structure of processing resources. So task evoked, meaning people are given tasks, and then pupillary response, pupil diameter changes in response to those different tasks. And the key here is processing load. So the tasks are different in terms of what kind of processing load people are exposed to. So let me give you one example from my lab. And that is an experiment in which we looked at human-human dialogues for spoken dialogues. So two people talk to each other. It happens to be between a driver, in a driving simulator in this case, and a remote conversant. So think of you're driving and talking to someone on the phone. We really wanted to know how cognitive load will change or be affected by switching between dialogue threads. So imagine having two different spoken tasks. In our case, 20 questions and the last letter game. So 20 questions game is a person is thinking of a word and the other person is trying to guess that word, and the way to guess it is to ask yes/no questions. And then the last letter game is I say a word and then you say a word starting with the last letter of my word. So here we have an example. The ongoing task, this 20 questions task starts out, driver says, is it used in the kitchen? So this is a yes/no question, and then the dispatcher responds no. And this keeps going, and at some point, there's an interrupting verbal task, this last letter game, and the driver says, dark, ends with a K, and then the dispatcher takes that letter K and says king, a word that starts with a K. That word ends with a G, so now the driver starts with a G, great. And in our experiment, both participants said 3 words each, and then once that was done, then they went back to the 20 questions game. And notice that in our experiment, in fact, we had parallel 20 questions. So the driver and the dispatcher shifted roles on each turn. So in this case now, it's the dispatcher's turn to ask a question. So the dispatcher says, does it have doors? And the driver responds yes, and then this keeps going until they're ready to take a guess. So let me show you a video of what this looked like in the lab. And I don't have sound here, so I'm going to narrate what goes on. So we have the driver who's in the driving simulator. We have the dispatcher who's this remote conversant, and you have the over-the-shoulder camera view of what goes on in the simulation. So you see it's a straight road. Okay, so is it in the kitchen? No. Does it have sharp edges? Says the driver. The dispatcher says no. And so you can see that there is this parallel 20 questions game going on. And you can see that the driver is driving on a straight road and keeping the car within the lane, following a car in front of him. And then at some point, the dispatcher will get a signal and switch to that interrupting task, word beginning with B, right? And now the driver says ball, and this keeps going, right? And so they're going to keep going doing this for 3 words. And then once they're done, they're going to actually then switch back to the 20 questions game. And then they're going to continue doing that. So, okay, he says, your turn to ask, right? So there's a nice little reminder. Does it have a door? No, yes, and then the game keeps going. Okay, so what did we look at? We looked, first of all, at pupil diameter changes. So on the left, you see a figure, and it shows you the pupil diameter for 20 questions part 1, before the interruption, then the last letter game, and then the 20 questions part 2 after they've returned. And what do you see? During the 20 questions first part, pupil diameter, on average, was lower than during the last letter game, and it stayed high, by the way, during the 20 questions second part. So this is telling us that, in fact, there is a higher cognitive load when you get this interruption, and it doesn't come back down after you're done with the interruption. So this is interesting. We also looked at the steering wheel variance and the lane position variance, because these are measures of how well you can control your car, and this is important, right? If you're going to have cognitive load, does it affect your driving? And it looks like it might. So look, 20 questions 1 has the lowest steering wheel variation, right? So this is how much does the steering wheel go from left to right, the angle, right? And this is an indication of effort. So you saw that the driver was supposed to keep the car on a straight road, and the more effort they had to put into it, the more the steering wheel variance will increase. So apparently more effort was needed once last letter came around, and then even more for part 2 of 20 questions. And look at lane position variance. So this is where is the car in the lane, left to right. And the lowest number was, again, for 20 questions part 1, but it increased and stayed high for last letter and then 20 questions part 2, right? So again, putting all 3 of these figures together, it tells the story that the interruption had increased cognitive load, and that can be seen in the change of pupil diameter, but also in these performance-related variables, steering wheel variance and lane position variance. Now, one thing I want to point out, though, is pupil diameter here is averaged over a relatively long period of time. So for each participant, we looked at 20 questions part 1 for each driver, right? And that might have been 5, 10, 20 seconds. And for that time, we averaged their pupil diameter. And then the average of those averages is the bar that you see here. So over some period of time, this was their pupil diameter. But we also noticed something else in the last letter game. And here, this is the figure that shows you that pupil diameter changes really quickly. And it can be used to assess the momentary cognitive load, not just this average cognitive load over some tens of seconds. So left pupil diameter for one particular driver, just as an example, look at how it changes between 308 and 311 seconds when that driver is thinking in response to the dispatcher saying dark, right? It goes up, pupil diameter rises, and then the driver says king, with K is the last letter of dark, right? So driver says king, and then look what happens with pupil diameter. It drops. And why does it drop? Because the driver doesn't have to be thinking about anything related to the game. They can just return to the driving, right? And so what you see here is pupil diameter responds really quickly to changes in cognitive load. And so the driver's pupil diameter drops until the dispatcher says great. And now the driver has to get back into that game, right? So the driver hears great, thinks of T, and then says tooth. You can again see that pupil diameter goes up while the driver is thinking about their response. So I think this is really exciting. Even on the order, this is 308 to 317, so this is about 10 seconds, right? About 10 seconds, and you see a rise, a drop, and a rise. So you can really get a fine understanding of what exactly happens with cognitive load as a task progresses. And here are a couple of graphs that show you that indeed during the last letter game, the mean pupil diameter, right, was higher when it was the driver's turn. So for the driver, when it was their turn to think, their pupil diameter was higher than when it was the dispatcher's turn to think, right? I also want to point out that the differences are really, really tiny, right? We're talking about a difference about 0.1 millimeter or even less. And that's my segue into my last slide here, which is that pupil diameter is affected by cognitive load, but really it's very much affected by light, as you might imagine, right? So we all have this experience of walking into a really dark room and needing some time to adjust, and that's because our pupil has to dilate. We also have the experience of when a bright light shines into our light, pupil contracts really quickly, right, to adjust to that. So another paper that you might wish to look at is our work on trying to separate these two effects. So how do you separate the effect of light, which is, by the way, the big effect, from the relatively small effect of cognitive load? And why would that be useful? Well, here's an example in this figure, right? So here's a person sitting in front of a computer, and we can see their pupil diameter. And what's interesting here is that they're looking at a screen. Well, who generates the content on the screen? Well, you as the programmer, right? The designer of the user interface, the designer of the learning software, the designer of the design software, right? MATLAB or whatever it might be that we're using, right? And so we can see how pupil diameter changes, and we can tell if it goes up or down. And we also know where the person is looking on the screen and how bright that spot is, because of course we generated the image that's displayed on the screen. So now if you can combine your understanding of where they're looking, how bright that area is, then you know, or in principle you could start modeling how should the pupil respond to the person looking at the bright or the dark parts of that screen. And then if there are any additional changes, well, that's probably because of changes in cognitive load. So the person might be looking at the screen and starting to think really hard about, say, some code or a design problem for a circuit, and you can see pupil diameter increasing because of this increased cognitive load. And you might make some decisions, for example, in learning software to support the learner, or in the design software and so forth. But you do have to realize that, pupil diameter is clearly cognitive load plus the effect of light. Okay, so that's what I have for today. And if you then come to the Human-Computer Interaction Lab at UNHEC, you will also be able to see some of this in action. So we have some remote eye trackers, like the ones you can see in this little sketch, but we also have some head-worn eye trackers. And if you come to the lab, then you'll get a chance to see how they work and how we can record some interesting data, and then how we can process that data. All right, thanks for your attention.